In this video, I just want to mention some important concepts about the Stork Enamine synthesis. It really builds off of the Michael reactions that we were talking about in the last couple videos. But we're going to do one trick, and as the name suggests, the trick will involve using an enamine, creating an enamine. Stork was the chemist, so that's the last name of the chemist who came up with this little trick. What we saw with the Michael reactions are that when you have an alpha-beta unsaturated molecule, the beta position is an electrophile. It's slightly positive. When you look at the resonance structures, in addition to the carbonyl carbon, the beta position is slightly positive. And so whenever you have these alpha-beta unsaturated structures, you really have two electrophiles. So an incoming nucleophile could attack either one. What we saw in the Michael reactions are that experimentally, weak nucleophiles tend to prefer this beta carbon, and strong nucleophiles tend to prefer the carbonyl carbon and react with that. Now we saw two versions of weak nucleophiles in the video on Michael reactions. We saw the Gilman reagents, which are really crucial, those dialkyl lithium cuprates. And then we saw this other one that we pointed out towards the end of the video, explaining the concepts behind the Michael reactions. It was where you have just one carbonyl. We said that this alpha carbon has hydrogens on it, and the hydrogens are acidic. A base can come by, steal the hydrogen, and those electrons could snap back onto the carbon there, and they would have a negative charge, but it would form still because those lone pairs, that lone pair would exist in a p orbital, and that would be parallel with the two p orbitals making the pi bond on the carbonyl, so the electrons can sort of spread out and be stabilized through resonance. But they weren't stabilized enough. This is actually still a strong nucleophile. It's stabilized enough for that to form. Normally it's hard to even get a carbon with a negative charge on it to form. So the resonance helps that to form, but even after it forms, it's a strong nucleophile. And so if we treated it with this alpha-beta unsaturated aldehyde or ketone, it would react with the carbonyl. And so what we saw was that to weaken it even more, we had another carbonyl on the other side. So that now, if you think back to those p orbitals, you have the parallel ones here, but now you have another pi bond, so you have two more parallel p orbitals, and the electrons can spread out over all 5 of those atoms. That alpha carbon is allylic to both of the carbonyls, and so resonance helps to stabilize that a lot, and so that finally becomes a weak nucleophile. This finally becomes a weak nucleophile and would attack the beta carbon, that beta electrophile of an alpha-beta unsaturated aldehyde or ketone, or system. So that's what we saw last time. Now the problem with that is that these molecules that have two carbonyls arranged like this, that share an alpha carbon together, those are not especially common. They're not as common as just regular old carbonyls are. So you run into, much more often, you run into this same molecule, but just with only one carbonyl. So, what if you still wanted to do this reaction? It's a really useful reaction. You're forming a carbon-to-carbon bond. What if you still wanted to attach this carbon, this alpha carbon, onto the beta carbon of an alpha-beta unsaturated system, but you only have one carbonyl? What can you do to this to make this a weaker nucleophile without fundamentally changing the carbonyl? And the answer to that question is given in the name for the Stork Enamine synthesis. You can turn the carbonyl into an enamine. Now remember, when you turn something into an enamine by adding a secondary amine. So that's an amine, and this is actually an equilibrium reaction. That's an amine. So nitrogen with all single bonds, that has 2 R groups on it. So this is a secondary amine because it's bonded to 2 carbon chains. And so only one hydrogen is there that can get replaced by the bond. You'll remember that can get replaced to replace this carbonyl. And you drew the mechanism for this on a previous test. And you'll remember that the product is an enamine. So this is an enamine. You have an alkene and an amine attached to it, so an enamine. Now the reason why an enamine functions as a weak nucleophile, whereas a ketone does not, it has to do with the resonance structures. So I'll draw those out here. In the case of just a regular old ketone, if you look at the enolate, that's what would be functioning as the nucleophile. This is allylic to this pi bond, so you can draw a second resonance structure where that moves over and these pi electrons move up. And so you'd end up with this structure here. So those are the two resonance structures for when you have that enolate, or when you have the alpha carbon just allylic to one pi bond. With the enamine, on the other hand, the enamine also has two resonance structures. There's a lone pair on that nitrogen, and that is allylic to this pi bond too. So the lone pair can go toward the pi bond goes away from the lone pair. That gives you the new resonance structure. And in this resonance structure, the nitrogen has 4 bonds, so it has a full positive charge, and then the carbon has a negative charge. Okay, so notice that when you form the enamine, in both of the resonance structures, the overall charge is 0. It's 0 everywhere on the resonance structure on the left, and in the resonance structure on the right, you do have a positive and a negative charge, but they even out. The net charge is 0. So this structure on this enamine is more stable than this enolate, because in the enolate, both of the structures have a full negative charge, a net full negative charge. And because they have that full negative charge, they are less stable. By stabilizing the carbonyl, by turning it into an enamine, in other words, this is less stable as an enolate, and this is more stable. Another way of saying more stable is it's less reactive. In other words, it is a weak nucleophile. So, we can take this molecule that we would love to do a sort of Michael addition with, and we can turn it in first into an enamine. After we turn it into the enamine, we can use the enamine as the nucleophile, use our standard reaction, and then just in the last step, hydrolyze this, because this goes both ways, hydrolyze it by adding the hydronium. So that overall, you would have something like this. You'd have just one carbonyl, so it's a really common thing to have, just one carbonyl. You would first create an enamine. If you use, you might remember from the mechanism that you should use an acid catalyst to make that happen, and also if you remove, to speed it up, and also if you remove water, that shifts equilibrium to the right through Le Chatelier's principle. So that increases the efficiency. And then you'd have your alpha-beta unsaturated molecule. So this would be a strong nucleophile. This first step turns it into a weak nucleophile. When you react it with this alpha-beta unsaturated molecule, it'll attack the beta position, and then to take the enamine off, to turn it back into the ketone, you just do an acid wash. So overall, you would get the ketone back, and it would just connect to the beta carbon. So notice this is the alpha carbon, the beta carbon of your alpha-beta unsaturated molecule. So it's a sort of beautiful workaround, a really clever workaround. So these reactions, these Stork enamine syntheses, are really going to be the same as the Michael additions. The one difference is that in the first step, we're going to turn the ketone into an enamine to make it a weaker nucleophile. And from there, it will just add the alpha carbon of the ketone onto the beta carbon of the alpha-beta unsaturated system. Otherwise, the first and the last step are always the same. So these are just a few concepts that will hopefully give you some perspective and some understanding on the Stork enamine synthesis.